So, what are visibility modifiers? In Java, these are keywords that set the access level for classes, variables, methods, and constructors. They are crucial for implementing encapsulation, which is a core principle of object oriented programming. By controlling visibility, we enhance security by hiding sensitive data and create modular and reusable code. The four visibility modifiers in Java are public, protected, default, and private. Let's begin with the public modifier. As its name suggests, public offers the widest level of accessibility. When a class, method, or variable is declared as public, it can be accessed from anywhere in your project, from the same class, another class, in the same package, or even from a class in a completely different package. On the screen, you can see a simple code example. We have a public class named demo. Inside this class, there is a public void method called display. Because both the class and the method are public, we can create an object of the demo class and call the display method from any part of our application without any restrictions. And this is why the public modifier is typically used for methods or classes that are meant to be a part of a global API. Next up is the protected modifier. This modifier is closely tied to the concept of inheritance. A member declared as protected is accessible within its own package, just like the default modifier. However, it can also be accessed by a subclass even if that subclass is in a different package. In this example, we have a class named animal with a protected method called sound. Then we have a dog class that extends the animal class. Because dog class is a subclass of animal, it is allowed to call the sound method from its own methods like bark. This is a powerful feature for when you want to expose certain functionality to child classes for them to use or override, but want to keep it hidden from the rest of the world. Let's talk about the default modifier, also known as the package private. This is the access level you get when you don't specify any modifier at all. Members with default access are only visible and accessible to other classes within the very same package. Here the class default demo has a method show with no modifier written before it. This means it has default access. As a result, only classes that are also in the same package as default demo can create an instance of it and call the show method. If you try to access it from a different package, you will get a compiler error. This is useful for helper classes or methods that are only relevant to the inner workings of a specific package. Finally, we have the private modifier, which is the most restrictive access level in Java. When a member is declared as private, it can only be accessed within the same class. It is completely hidden from the outside world, including the subclasses. This code shows an account class with a private variable named balance and a private method showBalance. This is a perfect example of encapsulation. The balance data is sensitive, so we make it private to prevent it from being directly read or modified from outside the account class. Any interaction with the balance must go through public methods like deposit or withdraw, which are not shown here. This protects the integrity of the data and is a cornerstone of building secure and reliable code. This table provides a clear summary of rules we have just discussed. Public. As you can see, the public modifier has checkmarks all the way across. It's accessible from the same class, same package, a subclass in a different package, and any other package. Protected. Protected is accessible in the same class, same package, and in subclasses in different packages, but not from unrelated classes in other packages. Default. Default access is more restrictive, limited to just the same class and the same package. Private. And finally, private is the most restrictive, allowing access only within the same class. We'll be now doing a practical demonstration of Java's visibility modifiers using IntelliJ. First, let's create a new project. I'll click on New Project, give it a name, let's call it Visibility Demo, and ensure Java is the selected language. Leave all the other settings as default and click on Create. IntelliJ has now created our project structure. On the left, inside the SRC folder is where we will put our code. We need two files for this demo. The first will hold our main execution logic and the second will contain the classes we want to test. So right-click on the SRC folder, select New Java class and name it as Access Demo. And this file will contain several small classes, each designed to show a different modifier. First, we have a public demo class with a public method. The public keyword means this should be accessible from anywhere. Next is default demo. Its method has no modifier, which means it has default or package private access. It should only be accessible to the classes in the same package. Then we have protected demo. Its protected method is accessible within the same package and also by subclasses. To show this, we have a subclass that extends protected demo and calls the method from inside. Finally, private demo. It has a private string and a private method. These should only be accessible from inside the private demo class itself, nowhere else. Now let's create our second file. By clicking on the SRC again, select New Java class and name this one as main.java. This main.java file is our entry point. The main method here will try to create the objects of our demo classes and call their methods. It's set up to test each modifier one by one. With our code in place, let's run it. I'll click the green play button next to the main method here in main.java. Let's look at the output. We see public method accessed. This works as expected because public is always accessible. We also see default method accessed, and this also works because our main class is in the same directory or default package as default demo. And protected method accessed via subclass. This works because our subclass is allowed to access the protected method of its parent protected demo. Notice what isn't being tested yet: private access. That's because the code to test it is currently commented out. If it weren't, the program wouldn't even run. This is the most important part of the demonstration. Let's see what happens when we try to break the rules. I'm going to uncomment this line here, which tries to access the secret variable directly from the private demo object. Instantly, IntelliJ flags this with a red underline. This isn't just a warning, it's a compile time error. If I hover my mouse over it, IntelliJ tells me exactly what's wrong. Secret has private access in private demo. The IDE won't let us run the code because we are violating the encapsulation provided by private modifier. The same thing happens if I try to call the private method. This is the core concept of data hiding in action. We are protecting the internal state of private demo class from outside interfaces. Now I'll comment these lines so our program is valid again. And if I run the program once more, it works perfectly. So, to summarize, we have seen how public, default, and protected members can be accessed within the same package. And we have demonstrated how IntelliJ actively prevents us from accessing private members from outside their classes, enforcing one of the most important security features in Java. On this slide, we have a Java method called checkAccessLevel, which demonstrates how we can control the flow of a program using decision-making statements. This program doesn't loop, instead it makes choices based on the input value. The method signature. The method is defined as public void check access level int level. This means it's a public method that takes one piece of information, an integer named level, as its input. It doesn't return any value. The if-else if structure. The code first checks the value of level using an if-else if ladder. The line if level equal to 1 checks if the input number is exactly 1. If it is, the program prints private access and its job is done. If the number isn't 1, it moves to the else if level equal to 2 block. If the number is 2, it prints default access. The switch statement. If the level is neither 1 nor 2, the final else block is executed. Inside it, we can see a switch statement. There is another way to make a decision based on the value of level. Case 3. If the level is 3, it prints protected access. The break keyword is important. It stops the code from checking any further cases. Case 4. If the level is 4, it prints public access and then breaks. Default. If the level doesn't match any of the previous cases 1, 2, 3 or 4, the default case is triggered and the program prints invalid level. This is a great way to handle any unexpected input. In summary, this single method effectively uses both if-else if and switch statements to execute both different code paths on the integer value it receives. This slide demonstrates two of the most powerful concepts in object-oriented programming, inheritance and polymorphism. Let's break down the code to see how they work together. The base class. At the top, we have a simple class called animal. Think of this as our blueprint. It has one protected method called sound, which prints a generic message, animal makes a sound. Next, we have the dog class, which is defined as class dog extends animal. The keyword extends is how we establish inheritance in Java. This means a dog is a specialized type of animal. It automatically inherits all the accessible members from the animal class, including the sound method. Inside the dog class, we have rewritten the sound method. The override annotation above it is a clear signal that we are intentionally replacing the parent's generic implementation with a more specific one for the dog class. This version prints dog barks. Now look at the test polymorphism class at the bottom. The line animal A equal to new dog semicolon is where we see polymorphism in action. We are creating a new dog object, but we are holding it in a reference variable of type animal. This is possible because through inheritance, a dog is an animal. When we call a.sound, which version gets executed? Even though the variable a is of type animal, Java determines at runtime that the actual object is a dog. Therefore, it calls the overridden method from dog class. The output of this program will be dog barks. In essence, inheritance lets us build upon existing classes and polymorphism lets us use a parent class reference to work with different child class objects in a uniform way, with Java automatically selecting the correct specific behavior.